Welcome to the teaching video for the new VSpin spindle. Today we want to show you how to teach the spindle, and we'll be using this part as our example. Programming, planning and deburring. We'll use the outside contour of this part and show you the programming and data advantages that the new spindle has. Here we see the milling tool that will be used and an adapter piece to attach the spindle to our universal robot. The adapter is designed to allow the spindle to work at a 45-degree angle, thereby automatically reducing the amount of movement required in one axis and improving results. In this particular example, the 45-degree angle does not bring any additional benefit, but we will see this in further detail later. To ensure correct operation of the spindle, it is important that the hose length of the air supply from the maintenance unit to the spindle is no longer than 2 to 3 meters. If a longer length is unavoidable, then the diameter of the air supply hose should be adjusted to ensure a sufficient air supply. We will look at this in greater detail later and see how we can check this using the spindle speed. Here we see the installed spindle and necessary connections. We can see the air supply for the deflection unit, the air supply for the spindle and the data cable. At the moment the spindle beeps and the signal light flashes green. This means that the spindle is not in its zero position. This is solved by providing air to the deflection unit. So when we turn on the air supply, you can see that the beeping stops and the signal light no longer flashes. The spindle is now in its zero position, and as can be seen in the data, there is no deflection. We can now begin. Now the spindle is set up correctly and we've double checked the parameters, we can start with the first waypoint. When programming, the first waypoint should always be made tangentially to the part, so the spindle makes a parallel approach to the part. This is in order to avoid starting with a sudden unwanted deep cut. So here we move to the first waypoint. Once in contact, we can see the spindle's optical indicator turn green and hear the spindle's acoustic indicator beep. As soon as we pass the low threshold of reflection, the optical indicator flashes. This green flashing indicates that we're in the optimal threshold for the spindle. When we move closer to the part, the optical indicator changes and flashes orange. This indicates that the spindle has exceeded the upper deflection threshold. When we then move closer, the optical indicator changes and flashes red. This indicates a crash warning, and when we move even closer, the optical indicator changes to a solid red to indicate a crash. So this is a crash, we're at the limit of the spindle. This is obviously not a good position to be in. In the best case scenario, the milling tool will break. In the worst case scenario, the concentricity of the spindle can be damaged and require repairing. So now comes the practical part of the video, and that is the programming. We have set a base point which is outside of the working area. The spindle approaches a tangent to the part in order to avoid starting with an unwanted deep cut. This is also important in terms of achieving a high quality deburring of the part. So now we can set the first waypoint. So here is the first waypoint. We can see that it is good when we are in the optimal working threshold between 0.7 and 1.5 degrees. The spindle tells us this and flashes green. As we have a relatively straight path, we will try to cover this part with only one more waypoint. Here we see the spindle flashing orange. We are at 1.5 degrees, a little bit over, a little bit under, and we can see that we need to make some correction. When we travel back to the first waypoint, we can see that we are right on the threshold between the two waypoints. 2 waypoints still look possible, so we need to optimise the second waypoint, placing it a little further away so that we have the necessary space. .9 looks good. So let's travel the path again and observe what the maximum deflection is. As you can see, the path can be travelled within our desired 0.7 and 1.5 degree threshold. It looks good. We will now set the next waypoints using the same method. Here we have a position between two waypoints where we are outside of the optimal deflection threshold. It is only 0.05 degrees, but nevertheless it should be corrected. We can either change an existing waypoint or add an additional waypoint to address this. So if we travel the path again, we will see that changing an existing waypoint has given us the optimal deflection that we want. Changing an existing waypoint meant that we did not need to create an additional waypoint. When setting the waypoints, always make sure that the working point of the milling tool is correct. Make sure that there is enough cutting surface in contact with the part. We recommend travelling backwards and forward along the path to observe and check this. So that is basically the teaching process. Now we recommend travelling through all the waypoints again. First to check that the deflection of the spindle is optimised, and second to check that the cutting surface of the milling tool is optimised. OK, one point needs a little fine tuning, but for the first attempt and just 10 minutes work, the result is very good. The robot stops briefly at this point, as a waypoint was added here later. We can now run the whole thing a little faster, and it looks good. It is important to ensure that a constant feed rate is maintained so that the milling tool does not stay on any particular point for too long and cut too much. A correct and constant feed rate ensures good deburring of the part. When we are happy with the programming, we can turn on the air supply to the spindle. First we can check the spindle speed. As indicated, the spindle was turning at 33,000 revolutions per minute, which is in order, so now we can deburr the part. Whilst deburring, the VSpin has logged all data, which means we have a complete data log of what occurred during the deburring. We have the deflection data, we have the speed data, and can evaluate this data to determine if we can further optimise the working of the spindle. One should examine the deburred part to check that the resulting deburring is as desired. Is the cut nice and uniform, or is it too deep or too shallow in any locations? We have already taught the VSpin a good path to base the deburring of the part on. To ensure that the correct deflections and speed have been set, we will recommend analysing the data of 5 or more parts that have been deburred. Analysing this data, it should be possible to establish where the lowest speed is and optimise that. The maximum deflection can also be established and also optimised. The deflection for this part is optimal at 1.5 degrees. A buffer of up to 1.7 degrees is acceptable, but everything beyond that should be examined and optimised. To install a new part, all you have to do is reference a waypoint to give a calibration point for the position of subsequent parts. In this instance, we will simply move the spindle to the first waypoint and note the deflection, 0.6 degrees. Then ensure that the subsequent part has the same level of deflection on this first waypoint. You can use any waypoint for this. You may find it useful on a particularly complicated part to place the spindle on a specific point of importance and use the deflection from that waypoint. So now looking at the deflection, you can see that the part is not correctly installed. We were at 0.6 degrees. So with 0.64 degrees we are close enough and can go again to collect more data about the deburring of this part. Now we will deburr this second part. We definitely know that we were in contact with the part at a lower threshold of 0.9 degrees, and therefore we can now reduce the upper and lower threshold parameters by equal amounts to give us more headroom before we reach maximum deflection or worse still a crash. This provides more reaction time. Do not forget to save these new parameters. Here we can see both threshold parameters reduced. Let the VSpin run again. We can see that values move between 0.8 and 1.5 degrees, which means that we can try another deburring and then look at the results. Step by step we are optimizing and improving the deburring quality. Looking at the data log, clicking on the Read Save Data, we can see the first and second passes. In our first pass at these points, we were over the maximum deflection threshold of 2 degrees. This can be quickly seen by the 1 in this column. Looking at our second pass, we can see that our corrections have improved this situation. At one point we were at 1.86 degrees, all of the points between 0.9 and 1.8 degrees, and in general in the range that we want. So by working on 3 to 5 more parts, we can further optimize the deflections to achieve the optimum result. We can then see where the minimal speed and where the maximum deflection is. This gives us the information we need to achieve optimum deburring. We can also check the spindle speeds and set the minimum spindle speed to optimize the deburr finish. Those two values we now set to 27,000 revolutions per minute as the minimum speed. This includes a little buffer as the minimal speed has been 29,900 revolutions per minute several times during the trial runs. You can use this feature to observe when the milling tool is no longer as effective and needs replacing. Here this would be the case if the speed fell below 20,000 revolutions per minute. and we increase the maximum deflection to 2.1 degrees and save the parameters again. And then we are in a good position. We hope that this video has answered the majority of your questions about the teaching of the VSpin spindle. Please look at the frequently asked questions section of the VSpin website, or do not hesitate to contact us by telephone or via email if you require further help.